All right, so hello everyone, good afternoon. This is our final lecture of our course on Introduction to Quantum Computers. And in this one, we're gonna focus on the superconducting microwave qubits, and also we'll make a conclusion and summary of this course. All right, so I decided to build this presentation in the form of a summary of the course, and so we're gonna start with the some little discussion, like a reminder of why we need quantum computing, and then we will transit to the superconducting qubits. Right, so here is a problem of non-polynomial problems, which are problems that whose complexity grows non-polynomial in a non-polynomial way with the increase of a number of constituting elements. Okay, it's like a typical example would be a problem of finding the energy spectrum of an atom or energy spectrum of a molecule. If we increase the number of atoms in the molecule, the complexity grows exponentially. Other problems are, of course, for example, factorizing some big numbers, etc. So some problems, they are non-polynomial and they grow very fast with the number of elements. And this type of problems is fundamentally unsolvable by classical computers. Okay, that's why we need other approaches, and one approach is quantum computing. So apparently the first person who spoke this idea was Richard Feynman, right? And so he basically said that if we need to solve quantum problem, why we use classical computer? Why not using the quantum problem for that? And as I said, quantum computer is used or can be used for not only quantum problems, but also factorizing large elements, unstructured data search, as we discussed, right? The factorizing large numbers can be solved by Shor's algorithm. Unstructured data search is the Grover's algorithm. Then first principle calculations of atomic spectra, chemical elements, and etc. So a large number of problems, non-polynomial problems, can be solved by a quantum computer. And quantum computing is based on three key components. And we all discussed this in our course, and here is just a summary, right? So the first component, the first ingredient is quantum superposition. Okay, so if we have a quantum object and the object can take or can be in two or at least two or several basis states, like for example here state 0, state 1, it can be a larger number of possible states. We have to take into account all of them. Okay, and before we measure the quantum system, we have to consider both quantum states at the same time, simultaneously. Like the particle has a clone and the particle the particle and its clone take both of these opportunities. Okay, so for example, let's consider an arbitrary quantum element. It can be electron or photon, whatever, and this particle can take, for example, different paths in space, and we numerize them path number 0, 1, 2, 3, etc. So we have to take into account all of them and write the state of this quantum element as a vector is in the Hilbert space of n dimensions. Okay, and the total state, the complete state of the element will be the superposition of all of them, which can be represented as the products of, or the series of the products of basis vectors 0, 1, etc. Multiplied by the projections of the vector on the each corresponding basis vector according to the rules of linear algebra. And as I said, when we measure this quantum object, we do experiment. In the result of this experiment, the wave function, the psi vector, collapses to one of the possible basis vectors, 0, 1, etc., with some probability, which is given by the absolute value squared of the corresponding projection of the vector on the corresponding vector, on corresponding basis vector. In quantum computing, we don't like to deal with like system like this with multiple possible states of a single particle, right? We restrict the Hilbert space to 2 dimensions. It's still complex, but 2-dimensional Hilbert space, meaning that we have, or we deal with just 2 basis vectors. For example, 0 and 1. How it can be done? Well, for example, we can take a screen with 2 slits in it, and each slit selects only one possible path in the space. So we restrict our basis to 2 basis vectors, and then we can put another screen behind the first one, and it will lead to the appearance of such an interference pattern if we measure the system over the second screen. Right, so in this case, the psi vector takes only 2 terms, c sub 0, 0, c sub 1, 1, and the states, of course, are orthogonal, because if the particle passed through one slit, it definitely doesn't go through the second slit, and vice versa. So the states are orthogonal, and we can represent, we can use this system as a qubit, right? A system with 2 quantum selected quantum states. One example of a qubit has been discussed in last week when we discussed the quantum photonics, or photonics for quantum computing. So as we said, if you have a light beam and we consider one single particular photon, the photon is kind of not the photon, the wave function or the psi vector, psi state of the photon can be split into 2 paths, this upper path and lower path. And then if we combine them again, using another beam splitter, we can get, for example, 100% of probability for a photon going to the upper direction or vertical direction, and 0 probability of finding the photon in the horizontal direction, which is in drastic difference to the classical picture. Like, one would say, okay, the photon bounces off the first beam splitter with 50% probability up, 50% probability horizontally, and then bounces from the mirrors, and then again bounces off the second beam splitter again. So we would get like 50% of the photon going to the left and 50% going to the up in the classical case, and this would not change upon changing the difference between the paths. However, the experiment tells us that we get the interference pattern, and even in the single photon regime, we get this single photon interference when the photon interfere with itself. Okay, so a right picture would be like would be considering this beam splitter creating like two clones of the same particle. It's not two particles, it's just two clones of just one particle. When we measure the system, we would find just one particle here or here, but never two particles, never two photons. And the photon interfere with itself, which creates this 100% of probability, for example, for a photon going to upper direction. This is the clear demonstration of the existence of this quantum superposition, and it's also a nice picture that demonstrates how this superposition differs from the classical superposition of fields. Like, for example, if you have a resonator with two modes, and the modes can be orthogonal, and the total field in the resonator is the superposition of two modes. So this is superposition of two like realistic fields, just a sum of them, or vectoral sum of them. So here we sum up the quantum amplitudes, which kind of, so people still have some, like, people still discuss what these quantum amplitudes are, but this experiment, I particularly like this experiment because it demonstrates nicely this quantum nature of the superposition. And by the way, we have the system in our lab, so if one of you interested, you can stop by our lab and see, look, play with the system, get the interference, and see how the changing of these elements adjustment leads to the change of the interference pattern. So you're always welcome. And so this is one type of a qubit, a photon going to different directions. Other types of qubits may be more practically feasible or useful is the electron spin, either up or down, right, of some, for example, electron or ion, and some atomic states in atoms and artificial atoms, as we're going to discuss today. So I've got one question in the chat. In quantum, do we restrict the Hilbert space to 2D sometimes or often? So in quantum, in general, we don't restrict the space to two-dimensional Hilbert. However, in quantum computing, we prefer to restrict the space to two-dimensional Hilbert space, because the reason here is exactly like restricting the computational space of a classical computer to just two elements: current on and current off, right? Zero voltage and some value of voltage, which is logical 0 and 1. So here we also have the same logic. We prefer to work with 0 and 1 and quantum superposition of the two. However, there are some alternative approaches to quantum computing with quantum object with the larger Hilbert space. For example, with the three possible states. So it's a three-dimensional Hilbert space and four-dimensional Hilbert space. And very, very popular approach today is so-called bosonic encoded qubits. They use the quantum information encoded into so-called bosonic field, bosonic states, and those are systems with infinite number of dimensions of the Hilbert space. So there are different approaches, but qubit is the most popular today. Okay, so for the computing we need more than just one qubit, right? And as we discussed in the course, if I have two qubits, I can write the tensor product of the two, and from two qubits, two physical qubits, I get four quantum amplitudes for the state 0, 0, 0, 1, 1, 0, 1, 1. Right, and if the qubits don't interact, this state is separable, meaning that I can write this as a product of two states of two separate qubits. However, if they interact, they each quantum amplitude C00, C101, etc., they depend not only the state of the first one, but also on the state of the second one, meaning that we cannot anymore like split them, even mathematically. And if we add more qubits, for example, the third one, we got 8 quantum amplitudes for just 3 physical qubits. And if we continue this logic for n physical qubits, we get 2 to the power of n quantum amplitudes. For example, in the case of 20 qubits, which is rather trivial today, we got more than 1 million quantum amplitudes. And each quantum amplitude, by the way, is the complex number, so it gets real and imaginary number, right? Or amplitude and phase, alternatively. So you should multiply by 2. So I mean that if you want to save the quantum state of a quantum system composed of 20 qubits, you would need 1 million, or actually roughly 2 million bytes in your memory. Okay, and this scales by 2 as you add more and more qubits to the system. And for example, in the case of 2 to the power of 50, so it's a 50 qubit system, you get thousands or millions of terabytes, right? So it's a really huge number. So you cannot even save the record in the memory, right? You cannot record such a large number of quantum states in the memory of a typical classical computer. But this is just 50 qubits, also rather I wouldn't say trivial, but to today's the state of the art is 400 qubits, which is much larger than this number, and even larger than the number of physical particles in the universe. Such a large number it is, but already can be realized in the lab. So we've got another one in the chat. And qubits restrict the Hilbert space to 2D. Yes, qubits means 2-dimension, exactly. And 3-dimensional quantum objects, I don't remember. They get another name there. Not qubit, but something else. I just don't remember the name. All right, so the key component, the first one is superposition. Another one is the quantum entanglement, meaning that we can create some particular quantum states, like this one we discussed in the course, right? So, for example, if it would be the state of 2 qubits, it would be a Bell state. Otherwise, this is the generalized Bell state. And you cannot write this state as a factor of, like, a product of 2 states of 2 qubits, meaning that they are entangled. And from this state, for example, if you measure this state, you can physically imagine like a system of n qubits, like array of qubits. And if you prepare this state, either 0000 or 11111, so it's like a ground state or excited state or something else. So if you measure the system, the entire system, like an entire system, collapses into one of the possible states. If you measure just one qubit in the array, it leads to collapse of the entire qubit in the entire psi vector, psi state, to one of these possibilities, either all zeros or all ones. So yeah, so we call this quantum entanglement. And the last component of quantum computing is the interference. So the system of n qubits, as we discussed, contains 2 to the power of n quantum amplitudes, which is a huge number for a typical existing quantum computer already. Even cannot be saved to a memory of a supercomputer. However, when we measure the system of n qubits, we get the n bits in the result of the measurement, right? So it's an n bit number, and so we lose the most of the information that we encoded to the quantum machine, to the quantum system. And in order to get the information in appropriate way, we design the quantum algorithms, which are basically the subsequent of consequence of manipulations that we do with the qubits in order to achieve the constructive interference that leads to the desired or to the answer, basically, right? So we need interference to get the answer, and this interference is created via the quantum algorithms. All right. So, of course, any so literally any system can be used as a qubit in this or that sense. And we usually imply several requirements for the qubits to be used in quantum computing. And these requirements are the requirement of scalability, so the system must be scalable. The ability to initiate the state of the qubit, so it must be addressable and readable. Okay, and the system must contain or save the quantum state, so it must have long decoherence time, and we must be able to realize a universal set of quantum gates based on the qubit, etc. But I underline this word here, scalable. So this requirement of the scalability, I would say, is one of the most important, because there are many qubits or the systems that claimed as operating as qubits, but the systems like poorly scalable. One is, of course, photons that we discussed last week. The photons, linear optics, so linear computing is scalable, meaning single qubit gates based computing in photonic scalable. However, 2-qubit gates in quantum computing not scalable well. That's why we don't have a photonic quantum computer yet. But this brings us to the other types of qubits, and the most important one, and in fact the vast majority of today's quantum computers and all IBM quantum computers that we used for quantum simulations, are microwave superconducting qubits. All right, so we transit to the discussion of these superconducting qubits, and one of the benefits of superconducting microwave qubits, as well as any type of microwave qubits, there are several approaches to microwave qubits, is that the microwave area is very well developed today, because or mainly because it is well related to military, right? And this area got a great boost after the Second World War, etc. So all these military applications like radars, communications, etc. So all this boosted this area significantly. So here I put some two numbers. A typical frequency of a microwave field is 3 gigahertz, which corresponds to roughly 10 centimeters in wavelengths. So 10 centimeters in wavelengths, meaning that if our elements get the dimensions of half of the wavelengths, so we're talking about several centimeters. So it's very, very feasible to fabricate such devices, to manipulate with them. It's much more feasible than, for example, in optics, where the wavelength is a few hundred of nanometers. So it causes many problems with the challenges with the fabrication of the optical devices, as well as in RF, where the wavelength is several meters or even kilometers. So designing such systems would be complicated. So microwave is very feasible research area. And today we can generate microwave fields and microwave pulses with any desired shape using these microwave generators. Generated pulses can be wave-guided using, for example, such rectangular waveguides or microstrip lines like this one. All this, of course, very well developed and can be easily fabricated. So the generated microwave field can be also stored in a resonator, like a cavity shown here, or like a ring resonator made of this microstrip lines. And of course, radiated using some antennas and some other radiators. So it's a very well developed area, and in fact, any of these items, each of these items can be used for quantum computing and can be used as a qubit. Generator can generate, at least potentially can generate microwave photons in different states, and we can encode quantum information in wave guiding modes, maybe of different polarization, and antennas can radiate also photons of different polarization, different frequency, etc. But it turns out that the most appropriate platform for microwave qubits is microwave resonators. So microwave resonator is a system where we store energy, right? And we can encode the quantum information into this stored energy in a resonator. So if I take a simple case of a LC circuit, like shown here, so this is the metallic wire. So these sides over here, they correspond to inductance. So this metallic part, they get some inductance. And this part in the center works as a capacitor. Okay, and the standing field, the eigenmode of such a resonator is the interchange of electric and magnetic field stored in the inductance, electric field stored in the capacitor, and in time we have the transit of energy from one form to another form. Right, and this type of oscillation is very similar to what we have in mechanics for mass on a pendulum, or like a bob on a spring, like shown here, right? So if I excite this oscillator, it will oscillate with some frequency, and the kinetic energy of this oscillator will transform to potential energy of the spring, and vice versa. So it's very similar to the electric and magnetic field transition in the LC circuit. And the important point about a system like this is that the frequency of this oscillation of electric and magnetic field, or potential and kinetic energy, doesn't depend on the amplitude of the field. Okay, and this is called harmonic oscillator. So harmonic oscillator is an oscillator whose frequency doesn't depend on the amplitude of oscillation. Of course, this is just a approximation, and especially in mechanics, the parameters of the spring and etc., they depend on the amplitude, of course, but as long as these oscillations are small, they don't depend on the amplitude of it. So we've got another question which says, how is quantum information encoded into microwaves? Like, what would a 1 and 0 look like? So this is what we are discussing right now, right? But for example, 0 and 1 in microwaves could be a state with low energy and high energy. Okay, so for example, here we came to this picture of the harmonic oscillator, and if we quantize, so if we remove all the excitations, all the photons from such a resonator, we will eventually come to the picture with a ladder like this, which corresponds to the energy of an oscillator depending on basically the number of the photons. So if I add one photon, I would get from this state, from the ground state to the excited state, the first excited state. If I add yet another photon, I will transit to the third state, then to the fourth state. So if I remove all the photons from the resonator, I will find myself at the ground state over here, no photons, and then adding photons will make me go up by this ladder high and high. Okay, and unfortunately, these transitions, these states of a resonator can be used as a qubit for two main reasons. One is the dissipation, like resistance in LC resonator, or some kind of friction in the mechanical case. So this is first, dissipation. The energy dissipates. Quantum computing mechanics don't like dissipation. We need our system to be dissipationless, and this comes from the fact that, which we also discussed in the course, that all quantum operations, right, must be unitary, and unitary means that we can reverse the operation and we get the reversed or initial state. Like I have wave function in the input, then I apply the operator like a quantum gate, and I get some result. In order to this, like for the system to work in an appropriate way as a good quantum computer, I would say that if I reverse this operation, I would get the initial state. But unfortunately, no system perfect, right? So after applying this operator twice, I won't get exactly the same initial state, because the system is get some amount of dissipation, but the less dissipation, the better. This is first. And second, we don't like these equidistant states. So what we would like to have is, like, having one photon would cause our system transit from the 0 state to the state 1. But then if I try to add another photon, because so in this case, it would cause transition to the third state, upper. But in order to be able to use the system as a qubit, I would like to make this third state just slightly lower, so the second photon wouldn't cause this second transition to the upper state, because it's different frequency. Okay, so we need to make this equidistant states, non-equidistant, meaning that we need to make this oscillator anharmonic, So for now, so this oscillator is harmonic, we need to make it anharmonic. So we need to add some anharmonicity, which means nonlinearity, when the frequency depends on the amplitude. Okay, and in the best case, adding just one photon, just one quantum of excitation to the system causes or changes the system in a way that it doesn't trap any more photons in it. So how we do so? And first we address this dissipation issue. Okay, so dissipation, how we can get rid of dissipation. So dissipation can be managed by this effect known as superconductivity effect. Okay, so this effect has been discovered by Kamerlingh Onnes in the last century. So basically he measured the conductivity of or resistance of a mercury element, okay, upon different temperatures, and he noticed that the resistance of the mercury element drops down to zero. Later it was demonstrated that it's really zero here. Okay, so at temperature 4.2 Kelvin, which is exactly the temperature of the liquid helium. And so later we have, or people have discovered other elements with different transition frequencies called critical temperature of transition to the superconductivity effect. Okay, and mercury is not here, but aluminum is here. So aluminum is the most important material for quantum computers for many reasons. So it's a very feasible element, and etc. And the critical temperature of transition of aluminum to the superconductivity state is 1.2 Kelvin. So let me. Yeah, so different materials, they have different critical temperature of transition to the superconductivity state, and the aluminum is one of the most feasible and useful materials for this purpose. Okay, so one of the like known effects of the superconductivity effect is so-called Meissner effect. So the Meissner effect is the repulsion of magnetic field from the superconductor below the critical temperature. Okay, so no magnetic field penetrates inside of this superconductor, which leads to, for example, this famous experiment of levitating of a magnet over the surface of a superconductor. So the magnet causes the currents which create the magnetic field with the opposite polarity and with the same polarity, and the magnets repulse each other, so the magnet can levitate. And here is the recorded video of this experiment. All right, so superconductivity effect, we simply get zero of resistance, and as a result, these metallic parts, they become lossless, so no dissipation loss in the metals, and this leads to the dramatic increase in the efficiency of these elements. Okay, so in a laboratory, we can achieve these low temperatures, for example, using such a closed cycle cryostat. So here in this picture we see this Montana Instruments cryostat, and we have one like this in our lab. So this cryostat allows achieving the temperatures above 4 Kelvin. Okay, so any temperatures around 4 Kelvin achievable with this system. And if you look at this table, for example, materials like niobium or plumbum, they already demonstrate superconductivity effect at this temperature. So we can achieve the superconductivity effect in our lab. And the system is portable, is like the size of a big coffee machine. So it's easy to use and etc. Comparing to other systems which are used in modern quantum computing, this system is called delusion refrigerator because the operation principle of this machine is based on delusion of the isotopes of helium, right? So the picture over here demonstrates the exterior of this machine, and this one demonstrates the interior, the system that like placed inside of this shielding metallic cylinder. So it gets several stages. The several stages generates different temperature, lower and lower as you go down to the tip over here. And typically this quantum chip processor is placed at the very bottom of this system, where the temperature is the smallest. And it's a very challenging and very complicated system in using, and you can notice like how, I mean, the color, it's for example, this one is gold or covered with gold, because gold gets many useful features at low temperatures. For example, gold is very good in terms of thermal conductivity, and also it doesn't deform too much. So it's a lot of work has been done to design a system like this. Very exciting that we now have systems like this. At the same time, it's very pricey system. So in our lab, we already can do some cryogenic and quantum related experiments using much cheaper, but at the same time very powerful system of this cryostat. All right, so for now we started with circuit, right? The LC resonator composed of inductance and capacitance. We say that in terms of response, the response of such a resonator corresponds to the harmonic oscillator with equidistant states, and adding photons or excitations to this system promotes us from the 0 state to the 1 state, second, third, etc., depending on the number of the photons. Okay. We said that cooling the system down to below 10 Kelvin, for example, in aluminum, it is 1.2 Kelvin. When the metal transits to the superconducting state, leads to the dramatic reduction of dissipation in the system. So the system becomes much more efficient, and it becomes more useful for quantum. Unfortunately, it's not enough to cool down the system just to 1 Kelvin, for example. Why? Because even at 1 Kelvin, we get the temperature noise, the noise that is associated with the finite temperature in the system. Okay, so 1 Kelvin is still produces too much noise in the system, and we have to cool it down to below 100 millikelvin. That's why we use systems like this. So below 100 millikelvin. It's a temperature where at which we must work if we want to achieve quantum response in superconducting qubits. Okay. And all this, of course, depends on the particular frequency, operation frequency. And this less than 100 millikelvin is taking into account the frequency somewhere around 3 up to 8 gigahertz. Okay, if the frequency is higher, the temperature would be different, but that also implies some restrictions in terms of the electronics, generators, etc. So all this, including the frequency, the temperature, is a trade-off between many aspects, including the realization of the system, this engineering, the existence of the generators, the measurement facility. All right, so we cool down the system even below critical temperature, below 100 millikelvin, in order to get rid of the thermal noise. But we still have this problem of equidistant states. So how we can make the system unharmonic? Okay, so how we can bring some unharmonicity to the system? And it's done with a nonlinear element. And this nonlinear element is called a Josephson junction. Okay, so nonlinearity means that if you add just one photon to the system, it changes the system so drastically that it changes the separation, the energy gap between the neighboring states. Okay, and if you try to add another photon to the second system with the same frequency, it doesn't find the right state to transit into, because the frequency of this second state will be changed, it will be shifted. Okay, so such a nonlinear element, as I said, is called Josephson junction. So the Josephson junction is the junction of two superconductors, like two pieces of aluminum, separated by a thin insulator. And this insulator is literally like the thickness of about 1 nanometer in size. So, and the physics here is as follows. So so superconductor itself is a system, right? So initially above critical temperature, we have a conductor with many charged particles, electrons in it, right? Below superconductor, the electrons, they combine into a pair, and this pair is called Cooper's pair. Okay, so the Cooper pair, composed of two electrons, is a boson, because 1/2 spin plus 1/2 spin generates spin 1, okay, or spin 0. Anyway, it is a bosonic particle, and bosonic particle means it behaves like a photon, so it can tunnel through the insulator like this. Okay, and key point here is that the current through this junction depends on this quantum phase between the states of Cooper pairs from both sides of from the insulator, like here. And another formula is called Josephson's formula for the voltage drop across this insulator. Gives us the voltage drop as a function of the time derivative of this phase. Okay, so if you take the time derivative of this first formula by time and then substitute, you will get cosine phi times df or dphi over dt, right? And then if you plug in for dt over df over dt to the second one, you will get the formula that connects the voltage and current, and it will be the voltage. It will be the formula that reminds the voltage drop across the inductor. Okay, so this element, it turns out that this element can be described as an inductor whose inductance depends on the quantum phase over here, which in fact depends on the current. Okay, so this is the nonlinear inductance. So a Josephson junction can be discussed or described as a nonlinear inductance. So in terms of graphic representation on schemes, this Josephson junction is represented as a element like this. Okay, so it's a rectangle with a small cross inside, and this element, of course, gets the inductance as we discussed. But also, since this is the system of two parallel superconductors, it also gets some capacitance. So any Josephson element is described by its intrinsic inductance and intrinsic capacitance. And these parameters, of course, depend on the particular realization of this junction. Okay, so again, we got for a linear system, for a linear LC resonator, we get equidistant harmonic response, which cannot be used as a qubit because we cannot select only two transitions. Okay, in order to be able to use the system as a qubit, we need to select only 0 state and 1 state and disconnect, remove all other states, 2, 3, etc. So we need to truncate our Hilbert space to two-dimensional space. That's why we need only state 0 and 1. So we need to bring unharmonicity to the system. This is the reply to your last question in the chat. So we bring this unharmonicity with a Josephson junction, like shown here. Okay, so we simply replace this inductor with a Josephson junction, which is a nonlinear inductance. Nonlinear means that the inductance of this element depends on the voltage or the current in the circuit. So the response becomes unharmonic, shown here, this blue curve over here, and this unharmonic, so in this case it's a sinusoidal profile, right? And this sinusoidal profile of the potential energy profile leads to the fact that the transition frequency from 0 state to state 1 differs to the transition frequency from the state 1 to the state 2. So these two frequencies now different. And if you work around this frequency omega 01, you would never excite the second transition, this omega 1-2 transition. And of course, this implies another restriction in terms of the bandwidth of the pulses that we use. And bandwidth implies the restriction on the duration of the pulses, and some systems, I mean, some particularly short pulses cannot be used because short pulse will excite other states, and the systems, these qubits, cannot be used in circuits with short pulse excitations, etc. So this is the matter of many trade-offs and practical realizations of particular system. Okay, so we can select just one transition if we work around this omega 01 frequency. Okay, and in this case, we sometimes refer this system as a superconducting artificial atom. So the artificial atom here means that we can design this transition frequency based on some tailoring approaches, right? So if we design the geometry, materials of these Josephson junctions of the circuits, we can design the frequency, operation frequency, and this is very useful, especially because usually like classical natural atoms that are also being used in quantum computing, by the way, their transitions are fixed or largely fixed. Here we can design this atom, this transition at our will. Okay, so we selected just one transition in our qubit by adding the Josephson junction to the resonator. So this transition is 0-1 transition. Okay, so 0-1 transition, and this is how a typical Josephson junction looks like after fabrication. So this is the electronic microscopy picture with the characteristic size, I believe 5-10 nanometers. So here we see two aluminum contacts, two aluminum superconductors, the lower one and the upper one, and a very small, very thin layer of isolator between these two. Okay. So we can isolate the two frequencies, the two states. What we can do with them? We can send a pulse, like an electromagnetic pulse, with some duration t, theta, and we can control this theta, this duration, this pulse duration. So there is a rigorous theory that describes these interactions, but the result is as follows. So in a simple way, the duration of this pulse creates the superposition between state 0 and state 1. Okay, so if I send a short pulse, the system will stay mostly in the 0 state. If I send a so-called pi pulse, the pulse with the time duration of the of pi. Okay, so it's it depends on the interaction of this transition with the field, but for any system, one can tailor this pi pulse, which excites the system from the 0 state to the state 1. So it flips the state from 0 to 1. And this is the realization of the X gate, right? So the X gate now, in this case, is just the application of a pulse with some particular duration. Okay, if I apply pi over 2 pulse, it will lead my qubit in the mixture of 0 and 1, in the perfect superposition of 0 and 1. And such a pulse is a Hadamard gate. So the difference between Hadamard gate and the X gate as well as other single qubit gates. In this case, in the microwave superconducting qubits, it's just the matter of duration of the pulse. We control the pulse duration, we control the quantum state of a qubit. This is very, very useful, very feasible, because as I said, these microwave pulses, they are generated and controlled with very high precision, and that's what makes this approach very, very useful for quantum computing. So yeah, so in this approach, the quantum gate, single qubit gate, is just a pulse with different time, with different duration. All right, and yeah, the control of this duration leads to the change of the probability of finding the state, the system in the upper state or lower state, and we can design it. Okay, so how in reality this control is realized? So here on this figure, this picture, all the way down on the right, you can see this Josephson junctions. Okay, it is zoomed area over here. So these junctions, they are coupled to a resonator, so-called coupling resonator. Coupling resonator, and this coupling resonator can be coupled to the rest of the circuit through so-called readout resonator. All right. So, and schematically, it's shown here. So we can have multiple Josephson junctions. For example, in this case, it is a system with two Josephson junctions. Then these junctions couple to the capacitor, this big capacitor, and altogether, capacitor and the junction, it creates the resonator, which is nonlinear resonator, and this nonlinear resonator is used as a qubit in this case. Okay, and then we couple this system through the coupling resonator over here, and yeah, so this is how we can control the state of a quantum system, a quantum resonator, and microwave qubit. So even at so low temperatures, the qubits still subject to some effects, right? Some external effects, some interactions with the environment, interactions with the vacuum field, by the way, which always exists and fluctuates around in the qubit. So all these factors lead to the transition. For example, if I excite my qubit from 0 state to the state 1, it will transit back after time t1. This has been also discussed in the course. This t1 corresponds to the population decay time, when my qubit decays from the excited state to the ground state. Okay, and even more important parameter is t2, which corresponds to the dephasing time, when or time over the time of loss of the quantum coherence of my qubit. Okay, so for example, if I excite the qubit into one state and it oscillates there with some phase in the excited state, after some time, namely t2 time, it loses the coherence and loses the quantum information. And this is because some random effects, some environmental change, the temperature, other things, and there are other, of course, reasons for the qubits, like shown here, to lose the quantum information, including the most important magnetic field noise, the trapped ions or trapped vortices, charge fluctuations, because the qubit must be fabricated on some sort of substrate, right? And the substrate is made of molecules, atoms, and those also fluctuate, and these fluctuations lead to the dephasing. And so in practice, we always strive to mitigate, to reduce the factor of these noises in order to achieve the better performance in terms of computing. So far we discussed only single qubit gate realization in the microwave circuitry. How we can achieve the coupling of two qubits? Okay, so if I want to couple, for example, two classical resonators, I would create a circuit like this, right? For example, I have the resonator 1 at the left, resonator 2 at the right, and then I can couple them through some coupling capacitors, right, with some switch in the center. So if I turn the switch on, the resonators will be coupled, and if I turn it off, they will be uncoupled, etc. In quantum circuitry, we can realize this switch using other Josephson junctions. Since they are nonlinear elements, we can control the way how they they couple other parts of the circuit. Okay, so for example, in this figure, we got this qubit 1 shown in blue. Again, it gets two Josephson junctions and one capacitor. We have another qubit 2 shown in yellow, right? And then we put this tunable coupler, which also gets two Josephson junctions here. And this tunable coupler can couple the qubits in a controlled way. Okay, so this is how we create the coupling between qubits, and this is how we can control the entanglement between the qubits. Okay, so this is the way how we can achieve this entangled states, Bell states, etc. So again, this is just a matter of some RLC circuitry and microwave design. And this is another beauty of the quantum microwave approach, because one can use typical circuitry design approaches to design the circuits, which is again very useful and powerful for. So, as we also discussed in the course, for the quantum computing, we need just 3 single qubit gates and 1 2-qubit gate in order to realize any quantum algorithm. Okay, so 1 qubit gate is realized through the application of 1 pulse with the control duration. If this pulse is pi pulse, then we get the X gate, right? If we apply the pulse with duration pi over 2, we get Hadamard gate, etc. How we can achieve this 2-qubit gate operation? So the 2-qubit operation, for example, C0 or control X gate, which we largely discussed and used in the course, simulated these systems using quantum computers. So this operation is also achieved by applying pulses, but pulses of different frequency. So now we have a system of 2 qubits. Okay, the qubits, they got slightly different frequencies, and we can populate one or another by applying the slightly different pulses with different duration and different frequency. So this is like in short how it works. So 2-qubit gate is just applying two different pulses to the system. All right. So this is schematically the structure of a quantum computer in a dilution refrigerator, right? So all the way down here at temperature 20 millikelvin, we get this quantum processor. Let's name it this way: quantum processor at 20 millikelvin. Then we can excite this processor using the usual KX cable. Okay, so this is excitation here. Since this excitation comes from the room temperature, it contains a lot of noise. So it's a noisy signal. And in order to get rid of this noise, we attenuate the signal strongly by a factor of 70 dB. So it's a very small amount of photons come to the circuit. Okay, the same way we can apply this control pulses over here and control the qubit. For example, we can realize this single qubit and 2-qubit gates using this pulses over here. And then we need to read out the state that we get after the executing the quantum algorithm, right? And so here we cannot use the attenuators to prevent the room temperature noise going down to the circuitry, because the signal itself is very, very weak. So we cannot put these attenuators, and instead we need to amplify the signal. That's why people use these different parametric amplifiers which work in the reflection mode. So we need to use some isolators here and circulators. So it's really a lot of work in terms of designing systems like this. Even just the task of readout of a qubit is a huge problem. Okay, and a lot of electrical engineers today work on improving all these things, all these parts. So, for example, these amplifiers, they need to be operating at 20 millikelvin, which is not that trivial by itself. And also these circulators and isolators, they also must be operational at 20 millikelvin. And so all this, I'm telling all this just in order to basically say that this area of quantum computing really needs people, engineers, with understanding of both of quantum physics and quantum computing and electrical engineering, microwave and RF circuit design and signal processing, etc. So it's a very, very multidisciplinary research area, and if you understand the both aspects, you will succeed. And yeah, so all this, for example, readout read out coaxial cables, right? If you have a system with many qubits, it requires many outcoupling channels like this with many circulators, isolators, amplifiers, coaxial cables. So all this leads to the huge amount of coaxial cables, facility, equipment, etc. And even for a system with 50 qubits like this one, it's already like a mess. A lot of wires and very complicated system. And but we need a computer with 1,000 qubits or 1,000,000 qubits. So one can imagine what a mess would be in that case. So excuse me. So there is a practical bottleneck of a scalability, so-called scalability bottleneck of a quantum computer. So it doesn't scale well, not only in terms of the number of qubits, but also in terms of coaxial cables, facility, equipment, and etc., etc. So there are a lot of challenges in this area, and there is a lot of potential work for future researchers and applied quantum engineers. All right. So in terms of existing quantum processors, today, so this slide, I took this slide from my last year presentation, and at that time, the state of the art was 127 qubits by IBM quantum computer. All right, and one can notice that the vast majority of the quantum computers, they are based on superconducting platform architecture, with just rare exceptions for photonic qubits, photonic computer here, and trapped ion here, but the most of them based on superconducting architecture. And as I said, this one, like the state of the art the last year, this year, it's already updated, and now we have the system with more than 400 qubits, fully entangled and machine. So you can notice the growth from 100 up to 400 just over one year. And in a couple of years, we're expecting a system with 1,000 qubits, and we expect this number to grow the next many years. So as I said, we need a system with at least a few thousand qubits to be able to do some practical things. And we're gonna get to few thousands in maybe 5 years or 10 years at most. And yes, so in terms of advantages of superconducting qubits, okay, so as we said, scalability is main advantage, because these qubits, they can be fabricated using conventional fabrication techniques, very well developed, etc. So this is like a machinery today. No challenge there. So one can fabricate a system with 1,000 qubits easily. And in fact, I know that there are some systems containing 1,000 qubits, but those systems are not fully entangled. Okay, so it's 1,000 but uncoupled qubits, which is still useless. We need 1,000 fully entangled, fully coupled qubits. The second one is controllability. Again, the single qubit gate, 2 qubit gates realized through the application of a pulse of different duration, which is very easily designed. So this another advantage of this approach. Readout speed. So all this, of course, is very well proceed with conventional electronics, and it can work at the terahertz frequencies. So the readout speed is one of the advantages here. Customizability, meaning that you can design the qubit at your will, and it will work at the frequency of interest. So that's another good thing. And of course, the resonators, I mean, the rest of the circuitry can be also very easily designed and customized. And compatibility with with classical electronics, right? It's an area that is very well developed today, and one can use this state-of-the-art electronics systems for controlling the quantum qubits. Unfortunately, we get several challenges here. One is the decoherence, unfortunately, and you can check, for example, on IBM Quantum website, the typical decoherence time, the T2 time of the qubits they used, and this is always somewhere around 100 microsecond, and this, of course, very short amount of time. And so decoherence is still a headache here. Another challenge is error rate, which is connected to the first one. If the qubit is sensitive to any sort of noise, you easily get error in response. Scalability limits, that's what we discussed. The scalability bottleneck, readout bottleneck, and other challenges apply too. So this system is scalable well, but until maybe 1,000 or few thousand qubits, but doesn't, or is not, ain't scalable well above this limit. So if we need a computer with million qubits, then we need something else. Cryogenic operation is a huge problem here, because it's not only the problem of getting such a low temperature, it's also the problem of the available space in the dilution refrigerator. So 1,000 qubits, it's already very tough to put them there, and if you need few thousand, 10,000, there is no space, and the more the number of qubits you put to the refrigerator, the larger the time of getting to the operation temperature, and the larger the energy consumption, and all these things. So still the challenge, and the huge challenge. And another one, the crosstalk and interference. So these elements work at the microwave frequencies, and microwaves get the wavelengths of few centimeters. So if you put the qubits like in the near field, like by a separation distance of few centimeters, they communicate, they couple to each other, they interact, and this is the interaction we need to get rid of to make the circuit operational in an appropriate way, right? So in order to be able to control each part of the circuit. So this crosstalk is another challenge. And of course, we have some advances in the area. So here I took this picture from our recent paper, demonstrating, first of all, demonstrating the progress, starting from the year 2000, roughly, when the first Cooper pair boxes appeared. So the Cooper pair box is like a system with Josephson junction, or so, well, the Cooper pair box is it works in a slightly different way. It uses the so-called the blockade effect. When you put one electron on an island, you cannot bring another electron because they will repulse, and the second electron will repulse the first one from the island. But still, it was the first type of the superconducting qubit. Then these flux qubits appeared based on the quantization of the magnetic flux through a coil. Then transmon is a typical type of qubit that is used today, and in fact, all the IBM quantum computers, they use transmons or different modifications of the transmons, and they already provide a much larger T2 the decoherence time of like around 10 or even 100 microsecond, which is much larger than 10 to the power of minus 2 microsecond, right? So it's already 1,000 times growth comparing to the pair box. And then other advances in this area include exploiting new alternative approaches, topologies like three-dimensional qubits. 3D qubit is a qubit where we still use Josephson junction, but placed inside a three-dimensional cavity. Okay, so it's not planar, it's a three-dimensional structure, it's a three-dimensional cavity. So the three-dimensional cavities, resonators, they have larger quality factors, and the most of the field is localized in the empty space, so the quality factor and the decay time of the qubit is greater, and some people work in this area. Other approaches include alternative ways to encode quantum information, for example, these bosonic encoded qubits, where you have this resonator, this cavity, three-dimensional cavity, with some photonic mode there. And you encode your quantum information into these photonic states. That's what I mentioned when I was talking about this, in the Hilbert space with the infinite number of dimensions. Right, so this is becoming more and more popular approach today, but still gets many challenges, including the size and the low scalability. The next one is new materials. Instead of aluminum, people try to use other materials in order to get like better response. New materials for the substrate. Okay, substrate is a huge factor because, for example, we cannot use the amorphous substrate. It must be crystalline, because amorphous, it gets this noise due to the amorphous state of the crystalline structure, and a lot of defects there, etc. And finally, error correction protocols. So what is error correction protocols? So the error correction protocols is simply encoding several physical qubits into one logical qubit. Okay, so instead of using one physical qubit for the computing, we use encoding of information into several physical qubits. Okay, and several physical qubits work as one logical qubits, and so this way one can improve or mitigate this problem of error. But unfortunately, of course, it requires more and more qubits. For example, this Shor's error correction protocol, it involves how many? 6, as far as I remember, 6 physical qubits to encode just one logical qubit. Okay, so you multiply the number of required qubits by 6, which is which makes this approach, one could say it's much less feasible than using just one physical qubit as one logical qubit. But still, there is a huge amount of work has been conducted in this area in order to get a perfect operation of a quantum computer. All right, and this brings me to the conclusion of the entire course. So in our course, we started with the basics of linear algebra, which is in the heart of the quantum computing, and not only quantum computing, but also artificial intelligence, machine learning, computer vision, basically everywhere. So linear algebra is very important area, and of course for the quantum computing it's paramountly important. So then we discuss the principles of quantum mechanics and all this quantum superposition, quantum entanglement, the quantum parallelism. We discussed the Bell states, entanglements. We discussed all these things, and then we transited to the quantum logic. We discussed the different single qubit gates, logic gates, and 2-qubit logic gates, their operation, the way how we generate the Bell states. We designed Bell states and simulated using the classical simulator and realistic quantum computer. We noticed the difference. We say that this Bell state experiment can be used as a benchmark experiment for testing quantum computers. All right, because this is a system with very well understood behavior, so we can deduce the reliability of the quantum computer in use. Then we transited to the discussion of various approaches to quantum computing. We started with quantum photonics. Okay, so this is a very scalable, very useful, system. The quantum information here can be encoded into different directions of propagation of the photon, or in different polarization of the photon, as well as some other approaches also exist. But unfortunately, the 2-qubit operations in quantum photonics is challenging because light or photons don't interact with each other. So we need to bring this nonlinearity using the nonlinear media, but this nonlinearity is very weak nonlinearity. Okay, so that's why there is no universal photonic quantum computer thus far. But if one creates a strong nonlinearity at the single photon level, that would be huge. That would be huge. And in fact, today, and including our group, there is a existing approach called exciton polaritons. Okay, so the exciton polariton is a system when you combine the resonance of a matter with the photon. Okay, and such a combined system, it already behaves as it demonstrates a strong nonlinearity even at the single photon level, but this work is still in progress. So hopefully we will get to the quantum computing based on photons as well. And finally, we discussed this microwave approach, microwave superconducting Josephson junction-based qubits. This is the most widely used system approach existing today. And we discussed the challenges and and the rest. So this area is very, very fascinating today because this quantum computing is just appears, and we expect to get more and more powerful computers soon. And as I said, the electrical engineers with the background in microwave, RF, and electrical engineering, circuit design, and in quantum physics can easily find their place, right, for their future, for their career. So this is it for today. Thank you very much. Let me stop there.